Hi everyone, welcome to the Central Library in Knauss Brown Bag series. Today our speaker is Doug Bell. He recently graduated with his PhD in marine science from the University of South Carolina, where his dissertation focused on marine phosphorus biogeochemistry, apologies.
There's three in there.
There's three in there. Currently, Doug is a South Carolina Knauss Fellow in OAR's Office of Policy Planning and Evaluation. Today he's going to give his talk, Elemental Stoichiometry, Insights into Coastal Nutrient Dynamics. Give it up for
Thanks for that introduction, Emily. And thank you all for coming out to hear me talk. And those of you online as well, thanks for participating remotely. I know you saw this talk and saw stoichiometry, and that's why you're here. You're just dying to hear about what that actual word means, probably to start with. So yeah, I'm going to talk today about a portion of my graduate research that I did. Fortunately, just published this work in Estuaries and Coasts, so very happy to talk about it with you today. There we go. I'm going to start with just some general background of estuaries and nutrients and those relationships and the dynamics there, the background story, and then the research challenge in itself, and then have kind of two different stories, stoichiometry, or the relationships between carbon, nitrogen, and phosphorus in the water, and then the stoichiometry of the fluxes of those nutrients as well, and those interactions and relationship between the two, and then end on just some takeaways. So I think we know the importance of estuaries and their coastal ecosystem services. Certainly important hubs of commerce and shipping, as well as hazard mitigation, storm protection. Estuaries are one of the most productive ecosystems on Earth. We get a lot of food and energy, very important for juvenile nurseries, as well as shellfish fisheries. And there's so much people in estuaries and the coastline, so really important for recreation and tourism economy. But what I'm going to focus on today is their ability to act as natural filters of nutrients. So that's fairly important when we think about coastal and land use change. These are two satellite photos of Charleston. The first one on the left is in 1984, and the next one on the right is current time. You can really see the increase in urban development to the northwest of Charleston. This is right along I-26, so you can see that urban sprawl just going back along the coast. And what happens when you turn this green infrastructure into gray infrastructure, you lose a lot of the natural ability to the environment to perform these natural ecosystem behaviors like nutrient filtration or any type of pollutant filtration. So what does that filter actually look like? You can think of the typical estuary. The river will transport water as long as with those materials, nutrients, other pollutants such as organic contaminants, more so now pharmaceuticals are becoming more and more important. So we have that transport from the land and then into the coastal environment. Typically this might be a salt marsh, but freshwater wetlands have the same kind of purpose. What happens here? All those nutrients get converted into organic material. It's reprocessed. There's a lot of transformations that go on in this area. And then eventually some is released back into the coastal water. So this is this filtration idea. And besides the pollutants that I just talked about, we're going to focus on nitrogen and phosphorus. They're two critical nutrients with water quality management. When you think about fertilizer, nitrate and phosphate, they make your grass grow, and then they get in the water, and they make things in the water grow. And really what we want to understand with this whole process is the fate of these two nutrients, right? And understanding the relative fate, and that's where the stoichiometry comes into play, that relationship between the two, is really important for understanding how these two nutrients work in tandem. So what happens when you break down of that estuarine filtration or any type of wetland filtration? I think we're aware of the consequences of excess nutrients. Here's some eutrophication from Chesapeake Bay, and that can happen at the very, very, very large scale. So this is the Mississippi River watershed, and all the agriculture and fertilizer, excess nutrients goes out into the Gulf of Mexico here. And following that eutrophication, similar here, all that growth and the breakdown of that growth sucks oxygen out of the water. So after eutrophication events, you get deoxygenated water. And the most common impact of that is massive fish kills. We're seeing that play out along Florida's coastline right now too. So tying in some of my research was trying to understand links of phosphorus cycling in the environment. One of the kind of grandstanding challenges in marine biogeochemistry and probably across all research areas is really connecting environmental behavior across scales, across spatial scales and across scales in time, right? Because often we study one component and want to make some inference about what happens at the larger environmental scale. So I was focused on understanding the molecular composition of phosphorus and how understanding these changes make an impact as we move up in environmental scale, right? So trying to understand the mechanisms here and what that means at the environmental level, the ecosystem level, and actually, at the global level. So I'm going to talk today about the environmental system right here using tidal creeks within a salt marsh as our model system. And really there's a lot of, when we look along our coastline, each of these estuaries or tidal creeks, they're all different, right? If we want to monitor and understand our environment, we need to know kind of the natural variation, the natural behavior of the system to really make inferences about management and other ideas. We can't study and understand every single individual environment. So we try to study one and make inferences about what that means for other environments. So like I said, understanding natural variability allows us to really understand maybe human impacts that would happen in the future, as well as impacts to climate change as well. So elemental stoichiometry provides a really convenient method for integrating the complexity for comparison between environments and just ongoing monitoring. So for instance, in our model Tidal Creek Salt Marsh, you have a lot of complex natural dynamics that change between environment. Just to name a few, geomorphology, the physical flushing of that environment, sedimentation, production, I won't keep listing them. But really to understand the behavior, we need to understand not just the concentrations and the amount of the nutrients, but their behavior with one another. So I'm going to be talking a lot more about stoichiometry and trying to explain it more and what that behavior means. So I have two questions that we'll talk about. We're going to look at variability over a temporal scale and look at the relationships between carbon, nitrogen, and phosphorus within a tidal creek estuary. And then using those measurements and inferences to understand the actual behavior. So you can think of question one as taking water quality samples and just getting kind of a snapshot picture, but you don't really know if that snapshot picture actually is what's going on. So the second part will be looking at some flux measurements and comparing stoichiometry between what we measure in the water and actually the behavior between the nutrients together. So this study was carried out within the National Estuarine Research Reserve System. For those that don't know the NERR system, it's operated and managed by NOAA. Its mission is long-term research, education, and coastal stewardship. There are 29 sites across the country, and we're going to be focusing on one of the programs within the NERR system. It's the system-wide monitoring program. And it was established in 1995 to understand long-term changes in water quality, air quality as well as changes in habitat too. So we're going to zoom in along the coast of South Carolina to North Inlet-Winyah Bay. North Inlet-Winyah Bay sits south of Myrtle Beach, north of Charleston. Winyah Bay is a riverine-dominated estuary, and that's kind of the typical idea of this estuarine filter. River transporting material into the coast. But there are other environments, North Inlet, which is a tidally dominated salt marsh estuary. So you can think of it breathing in and out of a tidal cycle. So material is transported in during the tidal cycle and then left again over the cycle. So it's still a lot of processing of nutrients goes on in these areas. So you've seen this photo before. Zooming in, this is that section of North Inlet right here, and you can see all the complexity and different sizes of the tidal creeks. And since we're going to totally disregard spatial variability, we're going to focus on oyster landing here, and maybe you can see within the creek beds and right at this station, you can see where oyster landing gets its namesake from. So to talk and back up maybe a little bit and just talk about nutrient cycling and just the basics of a nutrient cycle. We have dissolved inorganic nutrients. So I'll say these three fractions a couple times: dissolved inorganic nutrients, dissolved organic nutrients, and particulate matter. So think of the dissolved organic nutrients as nitrate, ammonia, phosphate, and this is like fertilizer for your grass. Those nutrients allow particulate matter to grow. These would be phytoplankton, algae, bacteria as well. In the salt marsh, you'll have that, those nutrients being taken up by salt marsh grasses as well. That particulate material produces dissolved organic matter or nutrients. That's produced either through growth processes of particulate matter, through cell death or grazing by zooplankton and things. And then dissolved organic matter or nutrients are eventually regenerated into the inorganic pool. They're also taken up by microbes as well. So this is the nutrient cycle as a whole. In typical water quality sampling, they'll either focus on just a total measurement of all of these fractions of carbon, nitrogen, phosphorus, or they'll focus on just specifically the dissolved inorganic fraction. So right here, nitrate, ammonia, and phosphate. And when you're trying to understand and incorporating stoichiometry and wanting to get this whole picture of how materials interact with each other, you really need to understand what's going on between inorganic nutrients, particulate matter, this relationship as well as this relationship. So to really understand the behavior, you need to sample for all pools. So what I did, I tagged on carbon, nitrogen, and phosphorus sampling to both of these pools with the base core system-wide monitoring program. So the sampling was done over a year long between October 2014 and August 2015. This is our site. This is it at low tide. This is it at high tide. And we're looking at two aspects of temporal variability. Over a tidal cycle, so these the swamp system-wide program does automated sampling every 2 hours. So you can see it right, maybe not see it right here, but there's kind of basically a bucket and bottles in this bucket, and it sucks up water. Automated, so we every 2 hours over a tidal cycle, so we get 13 samples total. And this the swamp program samples every 20 days. So we had 18 events in total sampled. So about 4 to 5 replicates per season. So you can see what this looks like when we sample over a tidal cycle. So this is complete semi-diurnal tides, going from low tide, where we have that colored dissolved organic matter, going into high tide, back to low tide, high tide, and then ending again on a low tide. So before I go into results, we're talking about tidal changes, seasonal changes, carbon, nitrogen, and phosphorus, dissolved organic, and particulate. So a lot to kind of put together. So with all the figures, maybe don't try to focus on the numbers. I'll try to walk you through each figure. And what we saw between all the relationships, I'm not going to explain every single one of the carbon, nitrogen, phosphorus, different fractions, just highlight a couple. But what we really saw is certainly variation within over a tidal cycle and seasonal cycle, but it was really a dominant of seasonal trends. So this is for dissolved inorganic nutrients, nitrogen and phosphorus. And what you can see here, in the winter, you have a lot of these outliers that pop up at the top with really high nitrogen to phosphorus ratios, and that's indicative of a precipitation event we had at the end of winter. So right north of the tidal creek is a forested swamp. So with precipitation, you bring in a lot of elevated nitrogen relative to phosphorus into your system. Moving into the spring, that relationship actually increases a little bit, so you have a lower amount of phosphorus. And what's going on here is you have a delayed release of phosphorus from the sediments. In the winter and early spring, the sediments are completely oxic, but as you have respiration occur over the year, or sorry, as you have temperatures starting to heat up going from spring into summer, you get increased metabolic activity, so you get increased rates of respiration. You turn those sediments anoxic, and that actually releases phosphorus into the water column. So that's what you see here moving into the summer. These relationships gets depressed back down, so where you have more phosphorus availability and actually rapid nitrogen cycling as well. So moving on to briefly touch on the particulate stoichiometry. Looking here on the left is the ratio again, but now we're looking at biomass as chlorophyll. And what we found was that it's got a seasonal component as well, but the stoichiometry really reflected the sources of material. So each of these dots is either a carbon-nitrogen relationship or a nitrogen to phosphorus relationship. So when you have low biomass, winter, springtime, you get ratios that are really highly variable. And this is indicative of detrital material. So detrital material comes from a lot of different sources with differences in N to P ratios, and they'll get processed over time. So you see a lot of variation here. And then when you get in the summertime, you get increased growth, biomass, and chlorophyll. This relationship really kind of attenuates. And what that does is it's indicative of growth of the dominant diatom community here. So just those two examples of the relationships that we found and can describe over a seasonal cycle. And the point I want to make about this study and stoichiometry is so often that the individual mechanisms of this environment are studied, either swamp drainage from a carbon and nitrogen perspective, or benthic release of nitrogen and phosphorus. But with stoichiometry, you're really able to combine all these different pieces of literature and studies into a coherent story. And not just a story, but actual quantitative cycling of these elements, so carbon, nitrogen, and phosphorus. And so again, so say benthic release of nitrogen and phosphorus, you'll have many studies that just focus on that. And what using stoichiometry allowed us to do was really expand and look at all the fractions and be able to tie this story together, really understand the dynamics of what carbon, nitrogen, and phosphorus are doing in this tidal creek. So to highlight really a dominance of seasonal influence, and this approach really allows us to tell a better story of what's going on in the tidal creek, and actually having some quantitative numbers behind it as well. So like I said, those were just snapshots. We sampled the water, we looked at some relationship, we had an idea of what that behavior was. But let's actually compare, see if we can understand if what we measure is actually what's going on in the water. So we're going to be focusing on this little tidal creek called Crab Hole Creek. Oyster Landing sits right here. And very conveniently, after I started this project, we realized that there was a tidal gauge buoy attached to Oyster Landing. And this tidal gauge buoy was operated by NOAA, their Tides and Currents program. And what we're able to do there is get water level monitoring every 6 minutes. And that allowed us to couple that water level monitoring with our water chemistry monitoring. And what the water level monitoring was able to give us is these tidal height measurements that we inserted into a model so we can estimate changes in water volume over a tidal cycle, and then couple that in with changes of nutrients along those same time intervals. And that's how we get fluxes of nutrients in and out of this tidal creek. Okay, so we're just talking about this little tidal creek. Is either material being imported into it over a tidal cycle, or is it moving out of the tidal creek on a tidal cycle? Okay, so another figure to somewhat disregard the numbers. This is over time. Focus on what's above this blue dotted line is import, and focus on below is export of material. Each one of these dots represents a nutrient and an estimate of tidal flux over a complete tidal cycle. And so what we've learned about this seasonal kind of behavior over a tidal creek, we can apply it to the flux estimates. So looking at the winter, we see somewhat similar changes in behavior of nutrients, but then you can see some decoupling depending on the nutrient. And again, this is our precipitation event in the late winter. Moving into spring, we see some similar behavior between all nutrients. And then in the summer, and I understand that this is a different year, we're going back in time here, but in the summer you see some actual significant decoupling between nitrogen and phosphorus. Moving on into the fall, you see some similarity in behavior, and then ammonia doing its own thing for a specific tidal cycle as well. So original idea was compare the water column stoichiometry that we measured with just the sampling, and then compare it with the behavior of flux. Okay, so in this table you see seasonal averages of the stoichiometry with the water column, and then below is the stoichiometry of the flux measurements. So fluxes that are positive, it means that nitrogen and phosphorus are behaving in the same manner. So what we can see here when we compare this, there's no variation that I applied here just to simplify the numbers, but in winter, spring, and fall, what we measured kind of matches up with flux. So we're measuring these ratios, and the nutrients are actually behaving in that manner. They're being imported at that same ratio, except for summer, right? So in this case, nitrogen is being imported and phosphorus is being exported, so you can see this decoupling, likely due to a surplus in phosphorus, right? Get a whole lot of release from the sediments. Nitrogen is being consumed, but there's a surplus of phosphorus, and that's being exported from the tidal creek, likely in the summer. So moving on to dissolved organic nutrient fluxes, kind of the same idea, but now we've added carbon into the mix, like dissolved organic nitrogen, phosphorus, and carbon. So again, import at the top, export below. We're curious on comparing the ratios between each other. And again, what you can see here, the precipitation event was really important for transporting organic carbon from the forested swamp and actually through the tidal creek and exported it out of the estuary. And organic carbon, because of its source, really rich in organic carbon relative to organic nitrogen, you see this decoupling of behavior. So you would not understand that just from looking at a simple water quality monitoring measurement. It really doesn't tell the story of what's going on. But in the spring, summer, and fall, these ratios somewhat match up with the flux ratios. In spring, both carbon and nitrogen are being imported. Actually, in the summer, they're both being exported. You can think of that as production of organic material, more dissolved organic nutrients. So you have a surplus there as well, but both behaving in the same way. And in the fall, carbon and nitrogen both imported into the tidal creek. And the last comparison I'll make is between organic nitrogen and organic dissolved organic phosphorus. And this is really what my dissertation was focused around, the differences between phosphorus cycling. And here you can see, right, these flux relationships are not at all similar to what's going on between dissolved organic nitrogen and phosphorus. And really probably the explanation for this is organic phosphorus, dissolved organic phosphorus, does not behave like an organic nutrient, right? It behaves like an inorganic nutrient. So you see a pretty clear decoupling of phosphorus as from this pool of organic material and behaving like a nutrient. And oftentimes we really don't consider DOP as a significant nutrient source, and that has implications for water quality management. So again, I want to reiterate, we just looked at temporal variability, and even just within one year. But within this salt marsh estuary tidal creek system, there's a lot of spatial variability. But the benefit of understanding or doing this study as a model environment, North Inland is really pristine, and we're able to understand the natural behavior of this tidal creek. And as I talked briefly at the beginning, when we have all these changes in land use, we really want to understand what the natural environment behave like. Because oftentimes with restoration, it's really challenging to return an environment to its baseline kind of concentrations of nutrients and whatnot. What we're really focused on, what we should be focused on, is that baseline function or behavior, right? We're often not going to return the system to its natural state, so trying to understand what that function of the system was is really important. And also this study helps us understand the capacity, the natural capacity of a system and how that might change over time. So I told you not to focus so much on the actual quantification of nitrogen input, but within that Tidal Creek over a 1 year, it was 2,000 kilograms of nitrogen, and some estimates of nitrogen assimilation from harvested oysters. That number is about the same as 8 million harvested oysters. And on an annual level, there's, I think I read, between 10 and 12 million oysters harvested from Chesapeake Bay each year. So think about this and just really the sheer power of the natural environment to process material. Certainly this number might not be the end fate of it, but it just kind of shows you the power in processing of these systems. So just to wrap it up with a couple more conclusions and considerations, the first point I want to make is this comprehensive carbon and nitrogen phosphorus sampling provides a lot of insight into the mechanisms of biogeochemistry and water quality dynamics, and should hopefully have considerations for water quality management. Of course, concentrations of nutrients are probably the most important thing, but understanding the ratios are really important as well. And we're actually seeing this play out in Florida right now. Florida in the Okeechobee Lake and its tributaries, we're seeing right now massive harmful algal blooms. And what that breaks down to is actually an excess amounts of phosphorus supply from fertilizer. Florida's geology is really nutrient poor in phosphorus. So when you have lower nitrogen to phosphorus ratios than the typical environment, the excess phosphorus supply is really driving eutrophication here. The specific type of harmful algal bloom here, it's the same type of harmful algal bloom in Lake Erie as well, and that has the same idea with the phosphorus supply. So really seeing this play out and will likely have implications for the political race right now as they focus on environmental protection. And the second point I want to make is the comparisons of stoichiometry, incorporating these flux measurements, which is really hard to do. It takes a lot of time and effort to understand the flux besides just basic water quality monitoring. And that allowed the evaluation of environmental behavior, evaluating our seasonal trends, showing the importance of stochastic behavior, these precipitations events, right? When do they occur during the year, and what does that mean for specific types of nutrients entering our watersheds? And then really nicely showed the decoupled behavior between relationships of nutrients. And hopefully that information, starting at the small scale, will really help us understand changes at the broader scale and ways for us to monitor and compare environments. So with that, if you want to fall asleep at night, you can please follow up with this paper. I won't even dare repeat the title of that. And then thank a lot of my collaborators at USC, my two advisors, Claudia Benitez-Nelson and Tammy Richardson, Jay Pinkney, Eric Tappa, and then at North Inlet-Winyah Bay, Dr. Eric Smith and Susan Denham, and then funding through the Baruch Institute and Sea Grant as well. So without further ado, I'll end there and happy to answer some questions.
Anybody have any questions in the room?
All right. Yeah, Bethany.
Great job. What kinds of concentrations are you guys seeing of nitrogen and phosphorus in this area, and do you know kind of where they rank on this?
Yeah, very low, very low. So, oh, sorry. Can you repeat that question? What is the relative amounts of nutrient concentrations in this Tidal Creek system compared to maybe other elevated systems?
Yeah, and how you would rank that on a eutrophication scale?
Low, very low. So that was the great thing about studying at North Inlet. It's pretty pristine. So I would say low as in 2 to 3 orders of magnitude lower concentrations than impacted areas, nitrogen and phosphorus. Yeah. So you can think of it as like 0.02 micromoles of nitrogen, and that number can get up into the 20 or hundreds for impacted systems. Danielle?
interested, but in the management side of this, or how, say, the state or someone would be able to use it. So, does South Carolina, like, do they currently monitor nitrogen and phosphorus there so that they would be able to tell, say, in Charleston, where there was the alpha development, that the stoichiometry is changing, patterns are changing?
Yeah, so what I would think for management, oh yes, what are the implications for management? How would you use stoichiometry to, I guess, improve your management strategy?
Yeah.
Yeah.
So it's like, if I was a water quality manager, how could I use that?
So if you're monitoring and you're seeing changes in more nitrogen or more phosphorus, or more specifically the type of nitrogen or the type of phosphorus, you can understand your sources of material. Maybe pinpoint whether or not that might be coming from non-point sources or point sources. And then just overall monitoring if you're making management decisions and changes. So some undergrad that work that I did at University of Michigan, there was a ban of fertilizers with phosphorus in them. So we were tasked with understanding the environmental change. How quickly would we see reductions in phosphorus in the water quality after that ban? So if you implement certain management strategies, you can track, you can kind of evaluate that change in management and see how that impacts the relationship between nutrients. Yeah, I'm still trying to think about it as well. Certainly with the natural variation and the concentrations, states are required, they have nutrient criteria to indicate healthy environments, right? And those nutrient criteria sets TMDLs. So understanding the natural variation, I think, informs how to set those TMDLs. Still, yes, that is a consistent challenge is trying to incorporate this into management strategy now that I'm moving away from the sheer technical aspect of it.
So you were studying at a tidal creek that, just because I know the system, I know is somewhat removed from the actual inlet itself. Is there any idea, so you're showing, like, what could be high levels of export from that tidal creek? Is there any way to know if that phosphorus is being used within the system, or is it actually just that the North Inlet itself is exporting a large amount of materials into the coastal water, so kind of deleting the system?
So the question is, how do you understand the end fate, I guess, of nutrients, particularly with respect to maybe phosphorus export? So in North Inlet, maybe 30 years ago, there was this outwelling study to really try to measure the exchange of nutrients right at the mouth, right? So the final fate of material. And I think it took about 200 volunteers for that study to be done. They were sampling completely overnight. So it's just really hard to measure flux. It's really hard to measure flux. And ideally, if you can kind of track a tidal creek from its maybe starting point and out to the basin, you'd be able to kind of couple that. You'd want flux measurements along the way. And I haven't, that was when I was looking through literature, you really had trouble finding that linking the exchange there with fate. So yeah, I mean, that's the whole challenge with spatial variability within a system. It's a big challenge. Did I answer it? Not really. Yeah, it's hard. Yeah. Sure.
You were showing the picture of all the recent development that's grown. And you mentioned that this is a real low concentration area. What's the secret of keeping the concentration of nitrogen and phosphorus low relative to big development?
What's the secret in keeping a environmental clean when you have development around the outskirts? I mean, ideally, you don't develop, or you limit development, because there's no like magical strategy for keeping it out.
I mean, this particular area.
Yeah, so let's say you had development, and this isn't North Inlet. Actually, let's see. So there's there's a development right here. I don't know if you can see it right here. But understanding the dynamics of water and where nutrients from that area might come into play would be useful to know. But limiting gray infrastructure and having a lot of green infrastructure would, I think, allow you to kind of buffer between a developed area and a natural, pristine environment. I think buffering is very important, and certainly practices you can do to I'll just leave it there. Yeah.
So is that the situation here? You just have a big buffer?
Yeah, big buffer. There's not a lot of exchange between this this community and, let's see if I'll go back to North Inlet. So this is all protected area. And so you even have separation from land right here. So Winyah Bay is actually pretty significantly impacted. There's a steel plant, a paper mill here, but surprisingly, there's only just a little bit exchange of this material of Winyah Bay water with North Inlet, probably maybe 5% water exchange a year. So yeah, buffer is very important.
We have a couple more questions.
Any from online?
Not yet.
Okay. Yes, Shelby.
So I have a question about the sources of nutrients. I know a little bit was from the swamp, but did you get any estimate if it was new material or coming out of the watershed to know what the challenge is in that area?
Yeah, so thank you for keep reminding me, Katie. What are the sources of nutrients? Is there an idea if that material is coming from the forested Swamp Creek, or is it coming from maybe riverine sources? Yeah, newer regenerated production. So again, this is a lot of the sources. I think a lot of coastal ocean nutrients, the concentrations of material and the ratios in North Inlet are pretty similar across the North Atlantic as well. So coastal nutrients, but I don't want to rule out the exchange that you get from Winyah Bay and traveling upstream a little bit. So it's a combination of everything. But when material gets brought in, especially the nitrogen, oyster creeks turn that nitrogen around rapidly. So it's really, there's a lot of ammonia in the system, and that has a lot to do with cycling of nitrogen by the oyster bed communities.
And that oyster turnaround is why you see low export, because there's too much nutrients?
Yeah, I think so. And it has to do with the age of the tidal creek. So that spatial variability within a tidal creek. Younger, mid-age tidal creeks have more import, and that's where you see a lot of the oyster bed creek developments, right? The mature creeks are more open water, and so that's where you see the export more. So yeah, a big nutrient demand by actually the bacteria in the oysters.
Sounds like there's some really great questions. Thanks, everyone. I think with that.
Yeah. Thank you so much for coming in and listening.